So the next speaker is Jacopo Borga from Stanford University, and he will speak about the skew Brownian permuton.
Okay, so thank you very much for the introduction, and thank you for the opportunity to be here. And so what I'm going to do today is to give a very brief overview about this topic of random permutation or random permutants. I will not focus that much on details, and I will profit of the fact that I'm at the beginning of the week, so whenever you want to ask me something more precise, you can come, and I will give you all the details. So the beginning of the talk is maybe known for some of you, but I want to be everybody at the same page, so let me start with very basic definitions. So my point of view on permutation is very geometric. It's random geometry, so let me explain it. So take this permutation, for example, 6, 2, 5, 3, 1, 7, 4. And this is the permutation that is mapping 1 to 6, 2 to 2, 3 to 5, and so on. So I'm using the one-line notation. And you can consider the permutation metric. That is, in the ith column, you put a dot at 8 sigma I, so that you have one dot in each column and one dot in each row. And I want to study limits of this structure. So this is not very convenient because it's still a combinatorial structure. I'll associate to it a probability measure on the unit square, where I replace in each box where there is a dot in the left-hand side with a uniform Lebesgue measure of mass 1 over n, where n is the size, such a way that the total mass is 1. So it's just a probability measure on the unit square, but for free, you get one additional property is that the marginals are uniform. In the following sense, if I fix a rectangle of sides b and a, the measure given to this rectangle is exactly b minus a. And this holds both for vertical and horizontal rectangles. So these kind of measures on the unit square are called permutons. They were first studied by a group of people involving Hoppe, Koyakawa, Moreira, Rolf, and Sampaio. And the reason was to a bit generalize the notion of graphons to permutation, and to study the fact that a good notion of substructure is enough to prove convergence in the permutant sense. And I will go in this detail. But let me give you first another very key definition for my talk. For my talk is the notion of occurrence of a pattern. So we say that we have a pattern pi in a permutation sigma if there is a subsequence of sigma that is order isomorphic to pi. So I never understood this definition when I saw it. Let me give you an example. So take this pattern 1, 3, 4, 2. You take the associated diagram. So 1, 3, 4, 2 is this one. And if you want to check if this pattern is inside this permutation, the only game that you have to play is to look at where if there are 4 points that have the same relative position. And that's it. Here there are 4 points. So we say that pi is a pattern of sigma. And the number of patterns that are permutation pi, the number of pattern pi that are permutation sigma is containing is the number of choices that you can have for these 4 dots, for orange dots. Okay, so this is the end of my definitions, very easy. If there are questions, please stop me. Otherwise, I will give you a very quick overview of some of the results that are known on permuton convergence. So pretty easy one. If you take a uniform permutation, the permuton limit, and here I'm taking limits with respect to the weak topology for measure. And okay, the limit is the Lebesgue measure, nothing very interesting. But there are several other models, and I will not give all the details. But what I want to say is there are very different limits. Like here, Dan Romick studied Erdos-Schecker permutations that are permutations where the length of the longest increasing subsequence or decreasing subsequence is exactly n in a permutation of size n squared. So what he shows is that there is a limiting curve. It's an algebraic curve of degree 4. And the scaling limit was determined where you have a density that is not uniform, for instance. Okay, this is another model that is called Mallow's model, where you pick permutation according to the number of inversion in the permutation. It's bias, it's a Gibbs measure. And here there are some pattern avoiding families. What do I mean with pattern avoiding? A family or a permutation is avoiding a pattern if the number of occurrences of this pattern is 0. So for instance, here we are avoiding the pattern 3 to 1. This means that in this permutation you cannot find 3 points that are in decreasing order. Okay, so it was generalized also to the case of any decreasing pattern. And in blue, what I presented here are some objects that are connected in some way with these families of permutations. I will not give you the details, but from this slide you have to take two things. Many models of permutation are connected with other interesting objects. And the second remark is that all these families have a deterministic limit. So for instance, for the malloc case, the limiting object is just a probability on the unit square where the density was explicitly computed. And looks like this thing. You know, you have a beta bias on being close to this diagonal, and it falls down when you move along the other diagonal. Okay, so many models were studied, or the limits were deterministic. And this is the first case where a non-deterministic limiting object was discovered. And it was discovered by Bassineau, Bouvel, Ferré, Gérard, Mazoun, and Pierrot in 2020. First in the case of separable permutation, and then in the case of substitution closed classes. So let's see a substitution closed class. So I have no time to define it properly, but let me give you an example. So this is what is called separable permutation, are the permutations that are avoiding these two patterns. And substitution closed classes are family of pattern avoiding permutation where the pattern that you are avoiding are called simple, are kind of prime permutation. If you want one quick way of saying if a permutation is simple is the following. You take the diagram, that in this case is a 4 by 4 diagram. You fix k smaller than 4, strictly smaller, like a 3 by 3 square. And there is no way that you find a 3 by 3 square where you have at least 3 points, exactly 3 points. Let me, if there is a chalk, yeah. So this is one of the two patterns that we are avoiding. And if you say a subsquare of size 3 by 3, at most you find 2 points, never 3. But okay, we don't care that much about the definition. Take the example of separable permutation. We need some technical condition on this class, but the result is the following. If you now fix sigma n a uniform permutation, yeah. No, it's a square. Yeah. Otherwise, you can clearly do it. Okay, because you have always 1 point in each column and in each row. Yeah, but in the square sense. So like here, I'm not taking in the book. Here I'm taking 1, 2, 3, and here I'm taking 2, 3, 4. Okay. And the result is the following. The permuton limit is a 1-parameter family of random objects that depends on a parameter p between 0 and 1, and I will come back here very soon. And it looks like that. So they are called biased Brownian separable permuton. It's a random permuton. It's a random measure of the unit square, and can be constructed directly from a Brownian excursion decorated with some signs. Again, I will not construct this object now, but I will tell you in the end, or a bit before the end of my talk, one way of constructing this object. So let me give you some simulation just to have an intuition on what this parameter is doing. So here it's Brownian separable permuton when the parameter p is very close to 0. And when you move to the right, it's increasing this parameter very close to 1. So as you can see, the parameter p is controlling in some sense the number of inversions of the permutation. Here we have very few inversions, so very few points that are in the wrong order. And here most of the points are in the wrong order. So as I said before, Mikkel-Mazun in 2020 give an explicit construction of this random object. You start with a decorated Brownian excursion when in each local limit, in each local minimum, you have either a plus or a minus uniformly at random, and all the signs are independent. And there is a deterministic procedure starting from this random object to reconstruct the measure. Okay, so this is the end of the overview. So if you have questions, it's a good time. Otherwise, I will move to another model. Okay, so what we did together with Mikkel is to look at Baxter permutations. Let me define them, and then I will tell you why we look at this model. So are permutations that are avoiding these two patterns. And if you pay attention, they are exactly the same pattern as separable permutation. But they have these red bars below. So this means that we have to avoid this pattern, but we require that 4-1 or 1-4 are consecutive. What do I mean? So let me give you an example. This is a Baxter permutation, okay? And the reason is, despite we have the pattern 2-4-1-3, this is okay, because 4 and 1 are not in consecutive columns. Here we have a permutation that is not Baxter, and this is because we have the pattern 2-4-1-3. Here it is 2-4-1-3, and moreover, 4 and 1 are also consecutive, are in 2 consecutive columns, and this is forbidden. Okay, so Baxter permutation is a larger set that contains separable permutation. Okay, so the definition is a bit folkloristic, I would say. But these permutations were already studied for some different reason. Mainly, it's because the enumeration of this family was open for several years. They were discovered by Baxter when he was studying the fixed point of functions that are commuting, and turns out that they are related to Baxter permutation. And there was also a work of Igor Pak and Dokush where they wanted to study what is the expected shape of this. So these are random permutations. In general, you expect that in the limit you have a random limiting permuton. You take the expectation, and the question is, how does it look like? Okay, they were trying to ask this question, but the techniques available at that time were not enough to answer the question. And what they did is to study doubly alternating Baxter permutation. It's a much simpler family. It's counted by Catalan number. And turns out that even if they didn't prove it in this way, it's deeply related to the Brownian separable permuton, the scaling limit. But what they wanted to do is look at Baxter permutation. And so let me show you here. We have 2 simulations of separable permutations. And here we have 2 simulations of Baxter permutations. So the first time that I saw them, I had 2 claims. This is not the Brownian separable permutation. But the second claim is it should be at least related to it. Maybe it's just a simple modification, because you have some, especially at the local structure, or at locally looks like a separable permutation, but there are some phenomena that were not typical of the Brownian separable permutation. And one of that is these big V's that you see here. So what we did with Mikkel is to prove what is the permuton limit. And we are not taking expectation. It's really a scaling limit result. So mu B is a random object. It's the scaling limit of uniform random permutation. And what we show is that Baxter permutation is not the bias separable permuton. The Baxter permuton is not the bias separable permuton for any choice of P between 0 and 1. And what we also did is to construct this object. And we constructed from a Brownian excursion, a 2-dimensional Brownian excursion in the quarter plane. And we use some families of stochastic differential equation. I will give you this construction in a few moments. in a much more general setting. But in a particular case of the general construction, we will obtain exactly this object. So once we had this result, one natural question was, okay, we have two objects. They are not the same, but are they connected? Is there a way to go from one to the other? Or can we find a common construction of all of them? And before doing that, since the construction is quite technical, let me give you at least the intuition from the discrete point of view. So the state of the art when we started at the project was a bit that one. So there was a very nice bijection between Baxter permutation and bipolar orientation discovered by Bunichon, Fusy, and Busquet-Melou. And there was a second nice bijection due to Scott Sheffield, Jason Miller, Richard Kenyon, and Wilson between bipolar orientation and a family of random walks in cones that are called tandem walks. So when we realized it, we were at the beginning happy. You said, okay, you compose in the right way these two bijections. You get a bijection from random walks to Baxter permutation. You study the scaling limit of the random walk. Everything is known. You transfer with some nice result, and that's it. Not really. There was a problem. One key feature to understand what is the scaling limit of permutation is the possibility to read patterns. That means if I give you index I and j, you have to be able to characterize if sigma I is greater than sigma j or sigma j is greater than sigma I. And in some sense, if you want to study the walk and then to transfer, you have to be able to answer the following question. If I give you the step, the I step, or a neighborhood of the I step and the j step, or something like that, and you can look just at the walk, can you tell me if when you apply the map, sigma i's will be greater than sigma j or not? And this is hard in general. If you try to find a characterization where on the walk, it's quite hard. And we had to take a slight detour on this map, and what we did is to construct two other maps from tandem walks to Baxter permutation. So this is what we called coalescent walk processes, and very quickly they are constructed as follows. So you take the tandem walk, and in red here you have just the y projection of the walk. So you look how the y coordinates are moving, and then you look at how the x coordinates are moving. You just draw them in the negative quadrant, so you take minus x. I shift them +1 and -1 just because I don't want them overlap with the green things. This is not important. And then you play the following game. You start at one of the black dots. And what you do is the following. If you are in the positive quadrant, you follow what the red walk is doing. So like here, I take this step because I'm in the positive part, and I take that. Okay? If I'm in the negative part, I just follow what the blue walk is doing. Okay? And there is a rule how to start. But the key point is that if one step is forcing you to go from the negative part to the positive part, there is a local rule that is telling, okay, you don't jump where the blue step is telling you, but you merge with the same walk that is starting at the same time. Like here, this walk was forced to go to 0. No, the local rule is telling to you, okay, you merge with the walk that was starting at time 9. Okay? It's just a rule. And what we prove is that if you look at these walks, this bench of walk like a tree, and you take the contour function of the tree, and you read the elements in this way, like, so I go here, this is the first element, this is the second one, this is the third one, this is the fourth one, and then here, this is the fifth one, and so on. I'm just turning around the tree. You get here a permutation, okay? It's 8, 6, 5, 7, and so on. And this is exactly the same permutation that you would obtain through these two maps, okay? There is a big advantage here, that now it's very easy to read patterns. Because if I give you sigma I and sigma j, or I and j, and I ask you, is sigma I and sigma j in this position or in that one, the answer is just you take the two walks starting at I and j, and you look if they are in this position or in this position at time j. Yeah. The permutation is just start here at the root of these three, and you turn around. So here it's 1, then you go here. It's 2. It's really the contour function of the 3. Yeah, exactly. That's what it says. Also the green, look in this direction. Okay, it's not important, but just to tell you, this is the K feature that we use to prove the scaling limit. Okay, so let me construct this limiting object. And you will see that there are a lot of things that are happening that are similar to the discrete case, but just in the continuum. So first of all, what I have to do is to consider a correlated Brownian motion. So you fix rho between -1 and 1. And a correlated Brownian motion is just a Gaussian process where x and y coordinate are Brownian motion, standard Brownian motion, but you have this covariant structure. And a correlated Brownian excursion in the quarter plane is exactly this process conditioned to start at the origin, and at the origin, and to stay in the positive quadrant. Obviously, like that, you are conditioning on a set of an event of measure 0, but with quite easy and standard argument, you can make sense of this construction, like the Brownian excursion, for example. It was first done in some very old papers, but the proofs that I know, there is one of Jason Miller and Scott Sheffield, and there is another one due to Denisov and Vashtel, just using scaling limit of random walks in cones. But I think you can do it also using just Girsanov theorem. So let me show you a bit how these processes behave. So here, rho is very close to -1. And why it looks like that? It's because, in some sense, the correlation is giving a bias on the direction that the Brownian motion wants to take. And -1 corresponds to the anti-diagonal. +1 corresponds to the diagonal, and you interpolate between them. So, as you see, when rho is very close to 1, you have a tendency to stay close to the diagonal. So, a natural model for the two-dimensional Brownian motion when rho is exactly 1, it's the Brownian excursion, because what I mean is that x is really equal to y. So I have the same coordinate, and I'm just looking at one of the two projections, and it's a Brownian excursion. Okay, so keep in mind that rho equal to 1, it's Brownian excursion. Rho equal to -1, it's defined as a Brownian motion, but it's not defined as a Brownian excursion because I want to stay inside this cone, but I'm really moving along this diagonal, and so I have no way, or at least no natural way, of making sense of this event. But let's keep in mind again, it's something that I would like to make sense. So maybe there is some way taking some sequences of rho n that is tending to 1 to -1 in an appropriate way. I will comment on that later. Okay, so now we fix a correlated Brownian motion between -1 and 1. Fix it like 1/2 or -1/2. And you consider the following families of stochastic differential equations. So here it's where people get scared normally. So let me go, it's easy. It's incredibly easy. I was also scared when I looked at them. But it's easy. It's nothing difficult. So you fix u between 0 and 1. And you consider this stochastic differential equation. Let's start with this thing here. Up to time u, the process is 0. Okay, everybody is happy, and okay, that's the end. No, so after time u, you move according to this dynamic. That is pretty simple. It's telling to you, if the process is positive, follow y. If the process is negative, follow -x. Here we don't care. Let's wait. Okay, we will move on. Take q equal to 1/2, and we are all happy, right? It's 0. Okay, so the story is the following. Here I have y. Here I have -x. I fix u, like u is here, and I construct this process that is just, when it's positive, it's taking exactly the same excursion as in the red part. When it's negative, I'm taking exactly the negative excursion of the blue part. And this thing is telling to you where you are at 0. You don't know what to do. And in some sense, this local time term is telling to you if you have to jump with a tendency on one quadrant or on the other one. This is the intuition, okay? Good. But I'm doing that for each starting time u. So what you have at the end is a monster like that. At each time u, you repeat the same procedure. Yeah. You have a natural interpretation of this local time in the discrete model, but not on Baxter. Because we will see very soon that in the case of Baxter, q is 1/2. So this local time term will cancel. And I can give you an intuition why. Did you remember that I tell you when you're negative and you're pushed to jump positive, you have this local rule that you do not take this blue step, but you merge with this one. And when you look at this kind of feature, you say, okay, maybe I'm destroying the random walk property, in the sense, when I'm crossing 0, I have a different rule. So it's not Markov, it's not, I have the same distribution for each step, but I have a local rule that maybe will pop up a local time. For some magic reason, in the case of Baxter, despite you change the rule, the law of one trajectory, of one green trajectory, is the one of a simple random walk with a specific geometric distribution for the jump. But in general, it's not the case. Yeah. No, there isn't in the other way, but in some other model there is. And I will tell you one model where there is. Okay, so I hope everybody is happy with this, but what you can get from that one is that now you have a bunch of processes for each starting time u between 0 and 1. And there is a problem. When you have SDE, it's not that easy to show that you have existence and pathwise uniqueness, so we have to prove it. So I prove it for the general case when rho is between -1 and 1 and q is fixed between 0 and 1. And let me say that this was already proved in the case q equal 1/2. So when you do not have the local time term. And this was a work of Prokai that showed pathwise uniqueness, and Paglar, RG, and Targer shows existence. I generalized this proof to the case where you have the local. And let me also mention that when you want to prove this kind of result, and what's annoying, it's also that you're dealing with an excursion and not a Brownian motion. But what you do normally is to prove the case of the Brownian motion, and then using continuity, absolute continuity result, you transfer to the case of Brownian excursion. But all of that, the step from here to here is quite standard. And here, it's mainly to combine techniques that are coming from these two papers together with the construction of what is called the skew Brownian motion. The skew Brownian motion is just a process that is constructed like follow. You take a Brownian motion, and for each excursion, you flip it as a positive or a negative excursion with probability p or 1 minus p. And this will give you a skew Brownian motion of parameter p, or here is q. Okay, so we have this, we fix rho and q, we take the solutions of this thing, and we get this bunch of processes, right? Pay attention, there is a little technicality. It's that the previous existence result was working for each q. So if you use Fubini-Tonelli, you can guarantee that this collection of processes is, for almost every omega, is defined for almost every u. So you might expect certain random time where you lose existence or uniqueness of the SDE. Never mind, we don't care because we are going to look at always set of Lebesgue measure 1. So these technical problems, at least at the moment, are not relevant. So just keep this collection of processes. And we define the following new process. It's defined as follows. So I'm measuring the Lebesgue set, the Lebesgue measure of the following set. There are two parts, a yellow part and a green part. The yellow part is measuring all the starting time of one of these processes such that at time t, I'm negative. Okay, so the yellow processes are in this set, are one of these processes. So this starting point will contribute to this set. And the green set is just, you take the work that is starting at time t, and you measure how much time is spending as a positive, in the positive part, okay? So it's a process, it's a random process. And the Subranium permutation of parameter rho and q is in some sense, okay, let me give you the formal definition, is the push forward through this two-dimensional map where in the first coordinate you have the identity, in the second coordinate you have this weird process of the one-dimensional Lebesgue measure. What I'm saying here, it's a very intricate and way just to say, take the graph of this function, and that's the permuton in such a way that the marginal are uniform. Okay? You take the diagram of this function from 0, 1 to 0, 1, and this is more or less what you see in the picture. Okay, so let me remind you that my existence and uniqueness result was working just for rho between -1 and 1, but 1 excluded. And the question was, can I do it also for rho equal to 1? And the answer is yes. You can do it exactly in the same way. The construction is exactly the same. There is a small issue. You do not have existence and uniqueness of the stochastic SDE that you are considering, but as soon as you can remember that in the case rho equal to 1, I'm just having one excursion. And again, you can show that if you decorate this excursion with some plus and minuses, IID, in the local minima, you can recover existence and uniqueness of the solution. So you have to do this little trick, but then after to this little trick, you do exactly the same. And what I also show is that this construction gives you back exactly the Subranium permutation, the biased Brownian separable permutation. Sorry. So another fact is that the Baxter permutation is exactly this object when rho is -1/2 and q is 1/2. Okay? So combining these two results, what we get is that we have a common construction of the two objects that we wanted to investigate. So are there questions about it? Otherwise, I will finally show you a bit how this object looks like. Yeah. Yeah. In the unconditioned case. Yeah. So let me say I was a bit sloppy, but when you consider if you drive this SDE just from a correlated Brownian motion, not a correlated Brownian excursion, you can make sense of the solution up to time infinity. After time u, okay, up to time u it's 0, but after time u will behave like a skew Brownian motion up to time u plus. Yeah, this is when you're driving with a two-dimensional Brownian motion. Here, solutions are not obviously skew Brownian motion. They are some kind of conditioned skew Brownian motion. And I have a lot of open questions about this, how this process is behaving in the conditioned case. Okay, so okay, here it's a simulation when q is fixed as in 1/2. Okay, when q is 1/2, you have rho very close to -1. It's -1/2, and it's the Baxter case. Here it's rho equal to 0, rho equal to 1/2, very close to 1 and exactly 1. So this is the biased Brownian separable permutation for q equal 1/2. And this is the Baxter permutation. Okay, and each simulation is an independent simulation. And here, what you can see is I'm moving again rho from -1 to 1, going down. And moving from left to right, I'm moving q from very close to 0 to very close to 1. And here, the simulations are not independent. Each line is constructed exactly using the same correlated Brownian motion that you see in the right-hand side. Okay? So I fix the Brownian motion, I fix q and rho, and I construct the corresponding logic. And again, okay, it's very clear, I think, what q is doing. It's biasing again the number of inversion, and this is something that we expect because we know that it's doing that in the biased Brownian separable case, and so since the construction now is common, it's pretty reasonable. What rho is doing, it's less clear to me. But my conjecture is that if you take rho that is tending to -1, and that's why I was saying I would like to have a natural definition of -1, I guess these measures should converge to something that looks like the Lebesgue measure. And then when you move, so if I would like to add the line here, I would guess that in the middle you have the Lebesgue measure. On the left and on the right, you are biasing from the number of inversions. So maybe if here the candidate is the bias separable permuton, maybe there it's the Mallows model. So one natural project would be to show that in the convergence we converge to the Mallows model. It would be nice because Mallows model and bias Brownian separable permuton are two of the most studied models, so it will interpolate among. And here it's when rho is equal to 1, exactly 1. So if I'm right, I'm still having 10 minutes, right? Okay. The last 10 minutes, I will switch to another topic. But before, let me give you a final remark. So here, we show that Baxter are converging to mu -1/2, 1/2, and substitution closed classes to mu 1q, right? This is our. So I was really sad about it. And why? I did this job, you construct a whole family of objects, and the only example that you know are both pathological. So why? One is it's having q equal to 1/2, so you lose the local time. And the other one, you have rho equal to 1, so you have a one-dimensional process. So you're doing a lot of mess for nothing. No, it's not true. It's because I took these other models that are called strong Baxter permutations that are avoiding this bench of pattern. And what I show is that the limit is one non-pathological skew Brownian motion. So there is hope that it's not completely useless. And what is funny is that the two parameters are the unique real solution of these two polynomials of degree 3. So, okay, so there is at least another model that is converging to this skew Brownian motion. And in the same paper, I show at least another model, and I presented, I didn't prove it, but I said using exactly the same technique, there is a bench of models that you can address. The unlucky part is that for each model, you have to do the computation for computing this one. And to compute this one, it's like 10 lines, maybe less, 5 lines. To compute this one is like 20 pages. It's really annoying to compute what is exactly the skew parameter. And the reason is that you have to take a discrete random walk and to look exactly at what is the bias of each excursion. And this is highly technical and annoying. But then, once you have done these technicalities about this parameter, the proof is pretty solid. It's working for a lot of models. Okay, so in the remaining now a bit less than 2 minutes, I want to show you another way of defining this model. So I define it starting from a Brownian excursion, but what you can do is to consider a pair of SLE curves. And they will give you back the skew Brownian permutation. So let me say, this equation is inspired from a reading group that we did in Zurich, where we proved that if you take two LQG surfaces and you glue them, what you get back, it's an LQG surface decorated with an SLE curve. This is called quantum Zipper from Scott Sheffield. And mainly I was inspired by this great result to prove the following. So I have to define very quickly object here, but let me try to do it. So we fix a parameter k between 0 and 1. Kappa prime is just 16 over kappa, and gamma is the square root of k. Chi is another parameter, 2 over kappa plus kappa over 2. Sometimes it's called q, this parameter. And then I fix an angle theta between 0 and k. I consider the complex plane with infinity and a Gaussian field on it. And then I take the flow lines of this vector field. These are done in the imaginary geometry sense. So what I mean, heuristically speaking, is the following. You take q squared, you fix an angle like 90 degrees, and then you take the flow lines of this vector field. What Scott and Sheffield and Jason Miller show is that if you do it for each point of q squared, these flow lines that are SLE kappa 2 minus kappa, these are SLE rho curves, they will merge and they will form a tree. Okay? Now you take the Peano curve, so the contour function in some sense. Okay? It's this green path that is winding around. And this is a space filling SLE kappa prime curve. Space filling means that it doesn't look like this picture. It's really something that is filling the space in a dense way. You're visiting every single point of it. And finally, I take an independent LQG area measure on this complex plane of parameter gamma. To be precise, you have to take a gamma quantum sphere. But it's independent from this Gaussian free field data. And now I'm parameterizing this curve in the following way. At time t, okay, I'm visiting a portion of the plane, because remember that this is space filling, so it's giving a part of the plane of mu gamma area exactly t. Okay, so let me do this game for two angles, 0 and theta. I fix time u, and the space filling curve nu theta, eta theta, is visiting a portion of the complex plane, like here. And then I do exactly the same for the other one. So there will be a time psi of u where the other space filling curve will visit the plane, like here, and I will hit this point at a certain point. Okay, so now one is moving from bottom to top, one is moving from left to right. And at each time u, I have a time psi of u where I'm hitting the point that was visited at time u by one of the two curves. So phi of u is the time when ni theta is visiting ni 0 of u. And the theorem is the following. If you take the natural permutons associated with this function psi, it's a skew Brownian permuton. And the parameter q is given uniquely by k and theta, but the function is not explicit. There exists, but we don't know the expression. And I have a conjecture about it, is to compute some weird probability of this condition skew Brownian motion. And rho is minus cosinus of 4 pi over 2. So one remark is that if you move k and theta in the range, you obtain almost all the parameters of the skew Brownian motion. The second interpretation of this result is a corollary that we obtained in a work in progress with Nina Holden, Tin Soon, and Puyu. And it's saying the following. Almost surely, however you fix x1 smaller than x2 and y1 smaller than y2, if you measure with the skew Brownian permuton the box with side x1, x2, and y1, y2, it's exactly the same of measuring with a Liouville quantum gravity this intersection of two things. Example, if I want to measure this area, I just need to take the skew Brownian permuton and measure this box. Okay? So this is the result. Summarizing, there was the skew Brownian permuton, there was the Liouville quantum gravity, there was the flows of SDE, and there was a river among them. And what I mainly did is to construct bridges. Okay? So now we know how this topic goes, but you know, when you have a bridge, and you don't use it, it's useless. It's a useless bridge. So what we are trying to do right now is to start to use these bridges. And the result that we obtained recently is using this bridge. So this connection between Subranium permuton and UV integrity. And the result is the following. It's again a joint project with Nina Holden, Chin Soon, and QU. And it's the following. Consider the Subranium permuton of parameter -1/2, 1/2. So the Baxter permuton. We were able to compute explicitly what is the intensity measure. So the expectation of the random measure is absolute continuous with respect to the two-dimensional Lebesgue measure, and it has a very explicit expression. I will comment on it in a while, but let me just tell you what are the key steps of the proof. Use the gold bridge, first of all. Secondly, there is a series of work, but the main one is of Morisang, Nina Holden, and Chin Soon about conformal wending of these into quantum surfaces. I was measuring things using quantum surfaces, but that were spheres. But you can look at a sphere like a quantum disk where you merge the two boundaries. And then they have some incredibly explicit integrability results for these surfaces. And using them together with some explicit computation for this two-dimensional Brownian excursion in cones due to very old result of Younger, we were able to compute the density. And as a remark, the intensity measure was computed by Michael Mazoun for the case of the bias separable permuton. This is the bias separable permuton of parameter 0.1, 0.4, and 1/2. And this is the new result. This is the Baxter permuton. It's much more smooth. It's much more smooth. We didn't prove it explicitly for the moment. I guess it's doable, but we didn't do it. And let me show you if this is this density and this is this density. Here I took some sections. Like here it's the diagonal section. And you see that one is having a critical point here, and the other one looks much more smooth. And there are the same events along different sections. So I guess my time is over, so I want to skip this slide. And maybe we will come back later. And so what I want to say as a conclusion is, OK, we build these bridges. We use that one, but I have many questions where my feeling is that this bridge is very useful. And I'm not an expert at all on this field, but I know that in this audience, there are many of them. So if you want, I have a lot of questions that from these can be translated here. And so let's try to solve them. Thank you.